Good afternoon. Welcome to this session, which is hosted by EDF, and it's Science as Sovereignty, why India must own the climate science agenda. It gives me great pleasure to invite the panelists, those who are present here, to the dais. May I ask Hisham, uh, Dr. Karthikeyan, Dr. Anup, Dr. Atik to please join here. I will take the last chair. Yeah, you can. Right. So, in case you are wondering why we should, in climate change, talk of climate science, nothing about climate change can be divorced from the climate science. And why science should have sovereignty, I think it will become clear down the line. But to just to set the setting correct, uh, the science of the very things which run on data, you do not have equal data at everywhere. That creates some issues with the interpretation. Also, there is always shortage of fund and more questions to answer or to explore. Then which one you choose also indicates your bias. And then many interesting questions which may be required for specific regions or for specific events tend to get ignored. But I think there is more to this dimension, not to talk of uh, deliberate downplaying of some of the ideas. So we have great panel, and we will also be joined by two very distinguished scientists, Professor J. Srinivasan, who is joining from Bangalore, IISc, and then also Sanjay Srivastava, who is currently in US, and he'll be joining from Austin. And of course, at Austin now it's 4 a.m., so we are grateful to him to join at this time. So to introduce the session, let me first invite Hisham Mundol, Chief Advisor EDF in India. And in this role as Chief Advisor, he is responsible for organizational strategy to demonstrate sustainable livelihoods in agriculture, livestock, and fishery, and as well as catalyzing the climate tech ecosystem in India. He is an economics graduate and a management postgraduate who started his career in sales, marketing, and consulting with Wordtel, the Unilever, Accenture, and Infosys. He has a vast and varied experience, and this includes setting up the operations in South Asia of Wikimedia Foundation, run a government program under National AIDS Control Organization, also leading the Children Investment Fund Foundation in India, which had the portfolio of health, nutrition, adolescence, education, girls, women rights, livelihood, child protection, and of course climate change. Hisham, the floor is yours.
Thank you so much. It's always a bit embarrassing to hear your profile and you're like, wow, I must be a rock star. First of all, I just want to welcome you all here. Mumbai Climate Week has 60 sessions. This is the only one dedicated to science. So congratulations for being a discerning participating group already. For those who don't know Environmental Defense Fund, just a couple of clarifications. If you're from the government and we say defense, we're not doing anything in military. If you're a funder, we're not a funder, we're an NGO, and so we're open for business. Let's talk science, and the headline is on the title of today's session is Science as Sovereignty. If you remember the blurb, what we had written was, if we do not author the science, we will inherit the rules. And in the climate era, the rules are written not only in treaties or in conferences, they are written in the models and the metrics and the technologies and the risk frameworks that shape how capital flows and how industries transition and how countries plan their very futures. When people hear climate science, you often think of satellites and graphs and academic papers. It is all of that. But beyond that, it is also in reality affecting very practical things. How do we design infrastructure? How do we price carbon? How do we assess climate risk? Which technologies get funded? And which pathways are seen as credible? In short, science has moved from the lab to the balance sheet. Now, consider India's reality. We are a monsoon-driven economy, a heat-exposed society, a water-stressed landscape, and a rapidly developing nation with enormous infrastructure and industrial ambitions. Yet, many global climate frameworks are built around temperate, industrialized, more prosperous contexts. Borrowed averages cannot guide a billion people decision. And that is where the idea of science as sovereignty becomes important. Not as scientific nationalism, but as scientific relevance. The idea is not to go against something that the rest of the world is saying for the sake of it. It means building our own data systems, our own models, and our own risk metrics so that decisions on water, agriculture, cities, energy, and industry are grounded in Indian realities and not imported assumptions. This becomes even more critical as we enter the era of climate tech and frontier sciences. From radical efficiency improvements to carbon capture to advanced modeling, emerging potential areas like solar radiation modification to data sciences in agriculture. These are no longer distant scientific questions. They are shaping finance, policy, and global governance conversations today. And the countries that shape the science behind these technologies will disproportionately shape the markets that follow them. India has a major opportunity here. We are sitting on one of the richest climate data sets on the planet. Decades of monsoon data, agriculture systems at scale, satellite and remote sensing capabilities, water, land, and climate variability across diverse geographies. Combined with our strengths in data sciences and engineering, this positions India not just as a user of climate knowledge, but as a producer of decision-grade climate intelligence for itself and for much of the global south. But if I may be candid, our constraint is not talent. It is investment, integration, and translation. What do I mean by these? In investment, we expect world-class scientific outcomes on relatively tiny R&D spending. Our private sector, while strong in technology adoption and scaling, still invests way too little in upstream and foundational science. On integration, too much of our excellent research remains in journals rather than becoming usable tools for policymakers, planners, and markets. In many ways, we are not science poor. We are science to decision constrained. Our institutional ecosystem is strong, from the ISC to IITs to IITM to ISRO, but it is still fragmented. Climate science today is system science. Atmosphere, water, materials, data, economics must work together, not in silos. And equally, as frontier sciences evolve, scientific capacity will increasingly determine who has a voice in global standard setting. If we are absent in the science, we will only be present in the consequences. So the question before us today is not whether India should participate in global climate science. Of course we should. The real question is whether we remain consumers of externally generated frameworks or whether we invest in domestically generating the science that reflects our monsoons, our risks, our development pathways, and our economic ambitions. Because climate science is no longer just about understanding the future. It is about shaping competitiveness, resilience, and strategic autonomy in a climate-constrained world. India does not lack institutions. India does not lack data. India does not lack scientific talent. What we now need is deeper R&D investment, stronger private sector engagement in science, better integration across institutions, and a sharper focus on translating science into decision tools. If we get this right, India will not just adapt better to climate change, we will help define the next generation of climate science, climate tech, and climate solutions for a rapidly changing world. Thank you so much for your time. I will pass it back to Vinayji.
Thank you, Hisham, for so eloquently setting the tone and the rationale for having a session on science as sovereignty. Uh, we have time constraint. We also have within 1 hour how many panelists can be also there. The panel itself has a very important constraint, which I think Hisham last week has written on IDR online, the limitations of panel. I think somebody will be sharing it with you, Tejas. What we want to do is start with a small keynote. And I feel privileged to invite Professor J. Srinivasan, a distinguished scientist at Divecha Center for Climate Change since 2016. He is also honorary professor at Center for Atmospheric and Oceanic Sciences in IISc. His earlier positions were chairman of Divecha Center for Climate Change between 2009 to 2016. He was chairman of Mechanical Sciences Division of IISc from 2005 to 2009. He was chairman of Center of Atmospheric and Oceanic Studies between 1996 and 2005. He obtained his PhD from Stanford in 1975. So there is almost a 40-year difference between the PhD of our senior most scientist and the youngest scientist. He did MS from the State University of New York in 1971 after doing BTech from IIT Madras in 1969. He also taught for some time in IIT Kanpur. Other than he has spent most of his career in Indian Institute of Science. He was also the lead author of the IPCC Fourth Assessment Report of 2004 to 2007, and he has been honored with many awards as well as Fellow of National Academies of Sciences and also the engineering. So ladies and gentlemen, I invite Professor J. Srinivasan to address the members of the audience on this very important topic. Professor Srinivasan. We'll share the screen. So yes.
Can you hear me?
Yes, we can hear you loud and clear.
Yeah. Is the slide
Yeah, slides will
projected
come.
to the
Yeah,
screen?
yes, yes, slides will come on the screens.
Yeah. So I'm going to talk about what should be India's climate agenda. Now, to understand that, in the next slide, we compare global climate change with local climate change. The global climate change is mainly influenced by carbon dioxide. But the local climate change depends on carbon dioxide, air pollution, local land use change, and many other factors. So we need to understand how India's climate will change in response to the global climate change. And in the next slide, I'll talk about the SWOT analysis of our position. Our strength is that our per capita emission of carbon dioxide is very low. And so we really cannot go lower than this. So to convince other countries, that is the weakness, convince other countries to reduce their CO2 emissions rapidly. So those are the strength and weakness. The opportunity is because we realize CO2 is a pollutant, we have started going in a big way to renewable energy, that is mainly solar. And this is very important for India because India does not have high quality fossil fuels or nuclear fuels. So solar is the only source of energy that we have easily. So it's good that we are embarked on this and we should accelerate this. The final issue is threat. Now, because of climate change, India is going to face more heat waves, more floods, sea level rise, as well as changes in monsoon. So we need to be prepared for these threats. Okay? In the next slide, I'm going to talk about the, I'm sorry, I'm not seeing the slide here. So the main question now is,
Sir, it is the lame excuses for not
you
acting
know
on
what slide
difference.
is showing right now?
Lame
I can't see the
excuses for
slide.
not acting on climate change. Yeah, Professor Srinivasan, uh, this is the slide uh, with title Lame Excuses for Not Acting on Climate Change.
Yeah. So the next slide I'm showing the kind of excuses that we get from other countries, the developed countries, about why they are not acting on climate change. Now, in the next slide, I talk about 4 major challenges that we face. One was scientific, which has been essentially solved by IPCC. We know that carbon dioxide is a major cause of climate change. The next issue was how do we mitigate climate change? There also we have been able to bring down the cost of renewable energy. So we are able to go from fossil fuels to renewable. The third is political challenge to convince politicians that we have to change. Now there we are not fully succeeded, at least in the international negotiation. Now the last thing is about social challenge. We need to convince everyone that we need to follow a path where we reduce our CO2 emissions. Now, the next slide shows why it is so important, because climate change is a threat multiplier. There are many things which are already happening, like heat waves, but now they'll be worse. And the next slide shows that because of climate change, in the last 2 decades, the heat waves have become 200 times more likely. So that is what is of great concern to us as a tropical country. Now, in March 2002, because of major heat wave, in the month of March, there was a large reduction in the yield of wheat in India. So heat wave not only affects human beings, it also affects plants and animals. Now the next slide shows that in India we face a combination of heat and humidity. Okay, and the y-axis is humidity, x-axis is temperature, and place like Bombay is very close to a critical threshold for what is called humid heat wave. Now, if the temperature goes over 1 degree or 2 degrees, many coastal regions of India will have situations where human beings cannot function outside. Now, the next slide argues that heat and humidity in the tropics are already reaching the limits for mammals. Okay? And the next slide shows how, because of the high heat and humidity, the productivity of agricultural work is going down. The x-axis is the wet bulb global temperature, which measures temperature, humidity, and the radiation. And y-axis is productivity is reducing rapidly. So this will have an impact on our agriculture. In the next slide, we also point out that for every vertical rise in temperature, the gross domestic product will go down by 12%. If the temperature goes up by 3 or 4 degrees, our GDP will go down by 40 to 50%. And the next problem we face is in the next slide. All the small glaciers in Himalayas are vanishing, and many communities which depend on these small glaciers are in deep trouble. Okay. And the last point I want to point out is the question of tipping point. In the next slide, I show tipping point wherein from the present climate, we may move to a new, more deadly climate rapidly, okay, not slowly. Now, if that happens, there could be very serious consequences. In the next slide, I show you the ocean circulation, which transports heat from the tropics to the poles, which is how Earth maintains its heat balance. Now, as the Greenland and other ice sheets melt, this circulation will weaken. Okay? When the circulation weakens, it has an impact on the monsoon. In the next slide, I point out that although the likelihood of decline of the circulation is very low, but the impact of that on the monsoon is very high. So the risk, which is a product of likelihood into impact, is quite high. So in the next slide, I have cited a paper published in 2023 where they estimate that the collapse of this Atlantic meridional circulation can occur in about 20-25 years, which is a very serious issue for India. Now, what will happen if it collapses? The next slide shows that if this happens, the monsoon system all over the world will southward. Okay, so a country like India will have a reduced rainfall by about 100 millimeters, which is equivalent to a drought for many, many years. So this is the issue we have to deal with. We have to convince all the countries in the world to try to maintain the global mean temperature to within 2 degrees as per the Paris Agreement. The last challenge we face is sea level rise. In the next slide, I'll show you areas of West Bengal and Bangladesh which will be inundated by sea level rise, which will result in large migration of people from those areas. And the next slide shows the threat to Mumbai, where this Mumbai Climate Week has been organized. Mumbai also face the impact of sea level rise, and so this shows the areas that are inundated by 2050. So in the final slide, I point out that India's climate agenda must focus on the impact of climate change and how we can adapt to it. And Mumbai Climate Week is an excellent forum to achieve this goal. And to end my talk on a lighter note, the Mumbai Climate Week in the next slide shows a cat saying that it has 9 lives. But human beings don't have 9 lives. And we have to learn how to deal with climate change and not let it control our life. Thank you.
Thank you, Professor Srinivasan. When we come to the QA section, again, I will invite your intervention. Thank you so much. And we will proceed with the next set of panel. Thank you very much. So, ladies and gentlemen, I invite the next panelist. He is Dr. Anup Mahajan. He is a senior scientist at the Center for Climate Change Research at Indian Institute of Tropical Meteorology. Dr. Mahajan obtained his PhD from University of Leeds, UK in 2009, and he had a MSc in atmospheric chemistry in 2005 from University of East Anglia. He also has a MSc in environmental science from University of Pune in 2004. He is winner of many scholarships, awards, travel grants and projects. His area of research is atmospheric chemistry. It is the trace gases and greenhouse gases and what happens to them in atmosphere and also their exchange with ocean and land. And his doctoral research was on halogen species in atmosphere. He has led multiple ocean expeditions to southern Indian Ocean. He has participated and has been PI to expeditions to Antarctica, Arctic. He speaks Hindi, Marathi, Gujarati, Spanish and some French. Today's lecture will, however, be in English. Dr. Anup.
Hello everyone. So today I'm here not to talk about Antarctica or teach you Spanish. I'm here to talk about climate models and how we develop them and why we develop them. So essentially, the institute that I work at is called Indian Institute of Tropical Meteorology, and there's the Center for Climate Change Research over there. And our job is to develop these weather and climate models. All of you get your weather forecasts from IMD, for example, and I know most of you tend to be skeptical about it, and there are good reasons for it. But the back-end research, developing these models which IMD runs, that's basically our job. And the way we go around this is we gather information from the world, and we try and make them into numerical formulas which we can then put into computers and get the outputs from them. Just to get like an idea from what exposure everybody has over here, does anybody know what was the first climate model that was developed? The very first one, somebody who projected that CO2 is going to warm the world. Any idea as to when it would have been? Would it be 50 years ago, 60 years ago? Ballpark numbers? 1930s, that's a very good guess because that's basically when we started getting a lot of information about CO2. But the very first projection, the first climate model was actually in 1896 by Swant Arrhenius. Everybody who's done chemistry in school must remember this Arrhenius equation, which gave us nightmares, right? So, that prediction of CO2 warming the world was actually done in 1896. So the physics of it was fairly well known. It's very simple. So, in theory, we don't need these big complicated models to prove that there's going to be global warming. You put CO2 in a room, it's going to get warm. It's very simple physics over there. But the implications of that physics is something a little more complicated, and that's why we need these climate models which can help us understand the implications of it. How is it going to manifest itself on our living world? And that's basically what we do. And there's been a huge revolution in the world of modeling. So essentially, the first models which we started doing weather prediction with after gathering information from the world was we started doing statistical modeling, which basically means like last 10 years, if this is the condition, then the most likely condition to follow it would be the average of the last 10 years, right? That's the data you have. So that's called statistical modeling. And that's basically what we used to do. And in fact, IMD used to use statistical modeling until the early 2000s. And those were the best models we had, which is why when IMD predicted that there will be rainfall, nobody carried an umbrella outside because they knew it was not likely to be correct. But from there, we made this transition to go from statistical models to numerical models, where we actually describe the physics in numerical equations. And that has really improved our weather forecasting. So now if you look at the skill of weather forecast models in India, the models which have been developed within India, the skill is almost about 75 to 80%, which is massive. And it's much better than any other model which does weather forecasting for the Indian region. This is where science of sovereignty comes in, because we are developing models specific for India, which focus on things like the Indian monsoon, which is a very exceptional phenomenon. It doesn't happen in most of the world, right? So we need data from here. We need models which are tuned for the nation itself, and that's the kind of work we do. In terms of climate modeling also, something very similar has happened. We started out with very simple models, which were just atmospheric models, where you put in CO2 and the temperature changes. These were global warming prediction models. But from there, we started realizing, no, it's not just the atmosphere, the ocean also plays a role. So we added the ocean in. Then we realized the cryosphere, the polar regions play a role. We added the cryosphere. We realized that the biosphere plays a very big role. We added that. We learned like the land moisture plays a big role. We added that, and so on and so forth. And so the models have gotten more and more complicated, which is why we need these big high-performance computing systems, HPC models, to run them. These are supercomputers. But if you compare the very first model and the models that we run now, the difference is like in mobile phones. Earlier mobile phones were like these chunky pieces which were useful for only one thing, which is for calling. Whereas now you're carrying supercomputers in your pockets. And that's the revolution that has happened in the climate world space. So our climate models have been getting better and better. And we've been developing very specific models based on what is going to happen in India, because the effects are going to be different from what happens in say, the mid-latitudinal countries, right? So for that, in IITM right now, we have developed our first Indian Earth system model, which is basically a model which describes as much as possible that we can of the world. Essentially, we are trying to simulate the entire world over here. So that's the kind of work we are doing, and hopefully what we can do is we can keep improving it. We are all the time we are adding complexity to the models so that we can make our predictions better, so that we have more confidence in what's going to happen, so that we can actually help policymakers understand with confidence what's going to happen in the future, so that they can put the policies and regulations in place. So that's the kind of science that we are doing, and hopefully, over the next hour, we'll have some conversations on why these climate models matter, how we develop them, and what uses it for the rest of the world. Thank you.
So thank you, Dr. Anup, for taking us from Arrhenius equation to numerical weather prediction. Our next panelist is Dr. Sanjay Srivastav. He is S. Radhakrishnan Chair Professor at National Institute of Advanced Studies, Bangalore. He was the Chief of Disaster Risk Reduction at the UN Economic and Social Commission for Asia Pacific, UNESCAP, from 2014 to 2025. He obtained his PhD in agricultural physics from Indian Agriculture Research Institute. Dr. Sanjay has been deeply engaged in strategic leadership roles in disaster risk reduction, climate change adaptation across Asia and Pacific, including as regional advisor at UNESCAP, head of the SARC Disaster Management Center in New Delhi, and he was earlier Deputy Program Director of ISRO, the Disaster Management Program. Currently, he is visiting US, and he is joining us from Austin, Texas at 4 a.m. in the morning. We are very grateful to him. Dr. Sanjay, please, floor is yours.
Thank you. Thank you, Dr. Mundol sir. My apology that I'm not there in person. I must appreciate this subject, science as sovereignty. It's such a passionate subject, and of the choice of the theme. So let me begin with a simple but urgent proposition. Climate science today is not just forecasting weather. It's about economic security. It's about development justice. It's about sovereignty. So we are living through a profound, a paradigm shift. I'm talking from a disaster risk reduction perspective. The shift is, for decades, we asked, what will the weather be? Today, the real question is, what will the weather do to people, to GDP, to infrastructure, and to food system? That shift from prediction to impact changes the role of science entirely. And this is what the needs and aspirations for building a resilient nation, most of the countries. Now, for the impact point of view, the shift is hazard forecast to impact intelligence, because disasters do not occur only because of the hazards, they occur because of vulnerability. So the question before us is not whether we can forecast cyclone or rainfall. The question is, can we integrate weather models with exposure, poverty, infrastructure, ecosystem stress? That's the translational science. Science that moves from hazard modeling to impact intelligence. Impact intelligence is the foundation of anticipatory governance, and that's the key. My next issue is, how does it matter for India? India loses an estimated 1.5 lakh crore annually due to climate-related disasters. The country protects the 11,000 kilometers of the coastline from the warming oceans, intensifying cyclone. Heat stress, flood, landslide, all these are now compounding. So disasters are not caused by hazard alone. So early warning system must evolve from hazard-centric forecasting to vulnerability-centric anticipatory governance. I would like to flag one very interesting publication, which is just last week, Physics Today. The publication was a key question. Why do disasters still happen despite early warnings? This is the lessons of European floods last 4 or 5 years. They have the best quality of the early warning system. Still, the casualties are very high. So major disaster with huge fatality. It's not because early warning didn't work, because of some other reason. And here in physics today, what they did, the science was systems are built to wait for certainty, while weather forecasts are probabilistic by nature, without certainty. So that's the gap. So weather forecasts are probabilistic by nature. Uncertainty is intrinsic to science. So the challenge is institutional. First, our governance system designed to act early, because the more early weather forecasts will have less accuracy. Do decision makers trust probability based forecast? Is risk knowledge embedded into our policy and finance? Based on all the lessons, the United Nations has come out what we call early warning for all framework. And here, the knowledge of the risk, then detection and forecasting, warning dissemination, that is risk communication, and preparedness and response. Unless you see all four together, it will be very hard to see the success of only climate science and weather forecasting. In this context, India's leadership in climate intelligence has been remarkable. India is not merely adapting global framework, whether it is the Paris, Sendai, it's also shaping climate science agenda. The most recently, you are all aware of Bharat forecasting system with 6 kilometer, 10-day predictive capacity. It's a game changer, AI driven landslide, flood forecasting, Himalayas, national pest surveillance system, coastal vulnerability mapping of the storm surge modeling of Bay of Bengal and Arabian Sea. This I would like to say with a lot of pride. This is an Indian model developed by IIT Delhi, Professor Dubey and his team, adopted all across Bay of Bengal and Arabian Sea, works perfectly all right, storm surge inundation model. We have transboundary seasonal outlook, South Asia climate outlook, third pole climate outlook, all led by India, and India models on the climate risk scenario. So these are some of the important contributions which came from these, what we call Indian labs, Indian mind. Now the AI is a strategic multiplier. This is what we need to capitalize on. It enables hyper-local risk analytics, because risk is always, adaptation and resilience is always local. Real-time agricultural advisory through Monsoon GPT, integrated physics, AI, flood modeling, urban heat stress mapping. These are some of the possibilities which we can see with the AI. Now the way forward, I would like to flag that the coupled hazard vulnerability modeling is the need of the hour, particularly from the disaster risk management perspective. Hyper-local risk database, which continues to be a constraint. In the beginning, Dr. Dadwal said the data are quite sparse, and hyperlocal is too sparse. AI integrated anticipatory governance system, which is emerging slowly. Climate informed infrastructure and fiscal planning, those are the things driven by the climate model. Transboundary climate diplomacy, particularly for many transboundary hazards. So the point which I would like to flag in the end was resilience is not a humanitarian add-on. It's an economic policy. Every avoided disaster protects development gains. Every anticipatory action reduces fiscal stress. Every early warning strengthens climate justice. So the last point, closing perspective is, climate crisis will not wait for certainty. The nation that will lead this century will not be those that predict hazard the best, but those who act earliest. India possesses the scientific capacity, digital infrastructure, and AI ambitions to lead the transformation. Final word, science is sovereignty, AI is the accelerator, anticipatory governance is the future of resilience. So these are the few thoughts from my side. Thank you once again for giving me this opportunity.
Thank you, Dr. Sanjay. Perhaps you heard it. There was a loud clap on your intervention. And as we are having the Mumbai Climate Week, we are also having the AI impact parallelly in Delhi. And please stay by in the Q&A session. We may require your further wisdom. Thank you, Dr. Sanjay. So we have now covered the climate change, we have covered modeling, we have covered the disaster and the vulnerability. Now that brings us to the monsoon and water. So I am very happy to introduce Dr. Karthikeyan Lanka. He is the Associate Professor for Center of Studies in Resource Engineering and also Associate Faculty at Center for Climate Studies in Indian Institute of Technology, Bombay. He obtained his PhD in Civil Engineering from Indian Institute of Science 2018. He has a Master of Science in Civil Engineering in 2014. He leads the Eco-Hydrology Research Group at IIT, dealing with measurements, modeling, and impact of precipitation, soil moisture, extreme dryness, and a whole host of issues related to water in the Earth system and its societal implication. Dr. Karthikeyan, please.
Yeah, hello everybody. So I'm going to raise a few points in line with what Dr. Srivastava has mentioned. So in the perspective of water, I would like to highlight the perspective of stakeholders in the first place. So when you look at these problems from the point of view of stakeholders, we have two things that will come into picture. That is the early warning systems, and second is the spatial scales. Okay, so the first is dealing with the time scales, and the second is dealing with the spatial scales. So especially in India, the stakeholders, majority of stakeholders are dealing with agriculture, and of course the urban population. So for both of these sectors, the kind of time scales that we need to focus on are quite different. That means, let's say if we are in Mumbai, we wanted to know what will be the situation of temperature or rainfall in the next coming few hours or probably days. Whereas when we go into agriculture sector, the target time scales would be ranging maybe from weeks to a month to actually plan for water resources and plan for the crops appropriately. So that's the reason why we need to target for these early warning systems spanning all of these scales, ranging from near real time to the seasonal time scales, targeting the specific stakeholders. So this is something that even the industry partners have to recognize, that whatever models that we are using right now, they are very well built for mid-latitude systems. They work well in Western countries or in the Europe. But when you start applying them over India, that's when you'll start to see a lot of uncertainty, a lot of biases. So these models have to be tailor-made for Indian conditions. And another biggest challenge that we have is the spatial scale. So whether you take urban sector or the agriculture sector, like what Dr. Srivastava has mentioned, hyperlocal scales is extremely important. Now, to build our ability to develop these forecasts at hyperlocal scales, we need to come up with better models, which means we need to improve the models which were already developed in Western countries. So we cannot just plug and play. So that is something that's very important. So industry has to support building these kind of models, which will be tailor-made for Indian conditions. And also, once we have these, even the physics-based models have certain limitations in terms of the extent of the spatial scale up to which they can produce the data. So beyond which, that's when the AI would come into picture. So where, which will help us to increase the spatial resolution of these kind of forecasts, whatever we are getting. So, but that's again where data sovereignty will come into picture. So we need a lot of hyper-local information. So the AI models would work well if there is more and more data that comes from these hyper-local scales. So this is where there should be a very strategic partnership that should exist between academia, government sector, and industry. So industry should recognize the support that's required in terms of the science-backed solutions, and there should be a lot of ground support, ground data that comes, which can be facilitated by government agencies. So with all of these three together, so we will be able to translate these forecasts to hyperlocal scales. And more importantly, we should not just focus on the hazard. It's, if some of you may know, we have this IPCC framework that characterize the risk. The risk is a combination of the hazard, vulnerability, and the exposure. So only when we take all the three factors in combination, we will be able to determine the risk associated with any hazard, be it heat waves, or droughts, or floods, or any extreme weather events. Even into our daily, day-to-day activities, even to plan irrigation, or even to plan our commutes, we need to integrate all of these aspects together to make meaningful information out of these forecasts. So that's the direction in which we need to progress in terms of making more science adaptable to Indian conditions. Thank you.
So thank you, Dr. Karthikeyan, and also flagging the issue with respect to data and data sovereignty. I'll just share with the participants here. You know, when you start late in the science, you have possibility of what is called leapfrog. This was a term which was used by Dr. Vikram Sarabhai when he said that India must do some space technology, although we were at that time in 66 not so well off. The other important point is look at the digital public infrastructure which has been raised in the past decade in the country, which makes your UPI globally the leader in the digital transaction. And this year, the government has put in money for AgriStack. So AgriStack basically contains one, all farmer identification, which have a code. Second, the second public layer of the AgriStack is each agricultural field is geocoded. And third, government has been doing crop surveys since 1865, the first wheat survey. From this year, on pilot scale, we have started what is called digital crop enumeration. So each field will digitally be allocated with a particular crop and available across the scale. So one could, in principle, write an app and get a hyper-local information. I think more will come to it, but that now brings us to the last intervention by our panelist, and we have covered climate, we have covered disaster, we have covered hydrology, so we will jump across the discipline and go to material science. I introduce Professor Atik Malani, who is at the Department of Chemical Engineering at IIT Bombay. He was a postdoctoral associate at Massachusetts Institute of Technology, Cambridge during 2010 to 12, and he was also postdoctoral research associate at University of Massachusetts Amherst during 2009-10. He obtained his PhD in chemical engineering from Indian Institute of Science in 2009, and he also has a MTech in chemical engineering from IIT Bombay in 2004. His research interests are materials for energy and environmental applications. He's a computational material scientist who uses a lot of high performance computing to estimate and model the properties of material, and his research is very relevant to carbon capture, utilization and storage. Dr. Atik, please.
Thank you, Dr. Vinay. So I have been asked to talk about on the CCUS. So by now in the climate week, you must have understood that the biggest culprit for the climate change is carbon dioxide, which is emitted. You might have the numbers, but just to give you a layman's perspective, we are emitting 38 billion tons per year annually. If you have to reference, if this is the bottle, we are producing almost 2 lakh tons, 2 lakh billion tons of this bottle every year. That is the amount of CO2 we are releasing into the atmosphere every year. In the Indian contribution is around 3 billion tons per year. Now, if one has to do the extraction, the capture, the capturing CO2 from the atmosphere is an important task. Again, to give you a visual analysis, if I hold this hand and if I have the air molecules inside, out of the 10,000 molecules of air, only 4 are CO2. Now we have this immense challenge of to identify those 4 and separate, and that is the capture. So currently the industry is using a technology which is called the amine scrubbing, very well known, developed long back, but it has the problems which will lead to the understanding that why this climate change or climate is becoming an issue, is that again, if you use, this is the scrubbing unit that you're using, in this, at a time you can have maximum 20 grams of CO2 that you can extract, 10% efficiency. So that is a capture, but what will we do? So you have to separate. Now if you have to separate, you have to heat this entire water bottle. That means you have to heat and remove the entire, and that costs the energy penalty. And that is the major problem in this CO2 capture, and because of which the cost of capture even today is somewhere around $50 per ton to $300 per ton, depending upon the geological location and anywhere. Now, if you multiply that to the amount that we are emitting of $38 billion, the numbers will come out to be around some trillions, 23 trillions of dollars in the worldwide. And for the Indian context, it will come out to be $239 billion, which is around 6% of our GDP currently. So you can see that it's a massive problem of how to capture. And this is the current challenge we have in CCUS, that we don't have enough technologies for this development, for this capture, and this is where the science is needed. This year's Nobel Prize went to one of these areas where it was on developing materials which can capture this CO2 very efficiently at relatively low cost. So that is the glory picture. Now, in terms of, let me not give you that bleak. There are efforts that has been done. I'll not go into the details, but there are worldwide around 77 or 80 operations are going on capturing this and then storing and utilizing this CO2. It cannot be utilized into any chemicals, but it has to be mostly done the sequestration. So that the positive aspect is that the policies at the worldwide level, people are thinking about it and coming up with the industrial hub model, where instead of each person for themselves, they are now partnering with each other and trying to find a together solution where you can use the resources and do that. So using this, as of now, the data indicates that we are sequestering around 0.5 billion tons per year. You remember the estimate, the emissions are 40 billions, whereas the sequestration is only 0.5 billion. You can say that it's a very small amount, but as somebody said, the Hercules was also a child at some time. So this is the same scenario, and with the hope that there will be more investment in this area, we will grow and become that Hercules. Now, for us, what is the current scenario? What do we need the information or the policy? So the most important challenge we have is that we need very good policy decisions, and a policy cannot be made if there is no backing by the science. So if you do not have a good backing by science, you will lose because you will make very bad policies. And if you have very good science, you can give a roadmap. So we need very large investment to develop those science at various level. This is the requirement at India, as well as this is the requirement whole worldwide. And that is required fundamental science in all level. Materials development for capture, the climate modeling, the emission modeling, and the sequestration. Those are the areas where we need all this, the lab scale and the pilot plant scales. The other, for the Indian context, we need is the lot of geological data so that we can identify where we can sequester that. That is very important. We have a capacity, but we have not identified that. So if we want to be a leader in this area, we need to invest in science and identify those positions where we can sequester. This is my 2 bits that in this area. Thank you for listening.
Thank you, Dr. Atik, for in very short time.
Reporter with Dialogue Earth. We focus only on environmental and climate journalism. And I have been doing a lot of writing on climate science, so this panel was particularly interesting. The question that I have for the panel, and anybody can take this question, is that climate science requires a lot of transboundary cooperation as well when it comes to data and research, especially with monsoon, floods, snowfall, droughts, everything. But the relationships between India and a lot of other South Asian countries are destabilizing at this point. What does that mean for scientists like you? What does that mean for scientific cooperation between these countries and for climate science in general?
Thank you. So this will be an enduring question. We will attempt. Yeah, second question, please. No, it's important to understand questions also. As much you understand the perspective. Yeah, please.
Hi, I'm Pavan Srinath from Well Labs. We work to transform water systems at scale across India. My question to the panel is, how do we ensure that sovereignty still keeps openness at the heart of it? I think we need to really embrace open data, public data. For example, with all of our remote sensing, how do we ensure that we take on gold standards of public data and ensure that sovereignty doesn't mean we close up, but we really open up and allow government, civil society, private sector, and others, local and international, to really collaborate? That's my question.
Yes, the third question.
I'm Marcela de Souza from the Watershed Organization Trust. I had a research unit over there. Our concern with the sciences are rather our interest in the whole integrated sciences. How do we take the science to local areas which are very unique, because the science at a lot of scale we get is rather large. And if we can simplify that science to reach communities, that's where actions can take place. That's an area that we also are working in. And we have an MOU with the IITM, and we do some work with them too.
Okay, we'll take the fourth question. I think one only here.
Hello everyone. Thank you panelists for understanding and making us understand what the background of climate science we are talking about here. But one thing which I am, not able to hear still in the questions is, where is the biggest polluter is playing in this science conversation? The industry still doesn't understand or back their decarbonization strategy based on the science analysis. So what's the stand on that? Thank you.
So thank you, participants. We had very interesting 4 questions on transboundary, and then we had the one on data, more collaboration, and the understanding or the appreciation by the industry. As you are aware, we have the World Cup going on. So I will try to bowl a googly, but I'm sure Hisham will make it a full toss. He will answer the question and conclude.
All right, so I'm going to try and answer some of your questions. On the transboundary point, it is true that at this moment, our relationships in the subcontinent are particularly challenged. It is also true that these things don't sustain over time. Things get better. However, even within this, an organization that comes to mind immediately is the Bay of Bengal program, which is Bangladesh, India, Sri Lanka, and the Maldives working on sustainable fisheries and coastal maritime. That's continuing to go strong. You will continue to find these kind of constructs, and I'm hoping that more and more emerge. I know we're not the diplomacy dudes, so can't answer the diplomacy question, but along the way you will continue to have those kind of cooperations. You're completely right on the sovereignty should not be closing, should not mean closing, being closed. 2 data points, which hopefully will assure you that India's general approach does not tend to be that. The way we shared the COVID vaccine when we had that capacity was actually quite remarkable. We could have, closed it there, but there was a lot more openness. The second is the whole architecture around UPI fundamentally shows that I am going to create open infrastructures. I will keep some things closed, which are the confidential bits. The fact that we're sharing a lot of this digital public infrastructure with sub-Saharan African countries suggests a nation that is, happy to do the kind of sharing that is there, but it is a constant challenge, the managing of the balance. On industry, the cement sector is just about the classic prototype of a high emission sector. What if I were to tell you that India's cement sector is amongst the greenest on the planet? Because 85% of the raw material is fly ash. 60% of the best, of the finest plants operate on renewable energy. 25% more energy efficient. Industry is getting the message. Industry is moving. Are all sectors moving as quickly as we want? No. Is there a lot more urgency that is needed? Yes. But they're beginning to see, if I'm a steel manufacturer, I cannot not think about emissions, because it means whether I can sell a gram of steel to Europe next year or not. It means whether I can sell a gram of steel in India in 10 years or not. So that's my attempt, and I tried to dodge one question. I did dodge your question. I'm dodging your question because I don't have a thoughtful answer, but I'm going to hope that, after this, the panelists might be able to give you a better answer than me. In the interests of time, let me just try and summarize. What we wanted to make the point today was why India should build more science. I hope in the course of this discussion, you got a sense of the bench strength that is available in Indian science. And these are just 5 scientists. And 2 things struck me. One was how much they talked about the politics and the social constraints as much as they talked about the scientists. No disrespect, but none of them were those classic eccentric scientists. They're talking implementation, they're talking industry. That is the kind of scientific strength that you have on the table. Some of them even have senses of humor, would you believe it? The message to the outside world is we need more investment in science. We need more priority on science from policymakers, from companies. We need more collaboration. It's so great to see, Watershed in a partnership with IITM as an NGO which may not have that scientific depth. Reach out to these universities or other academic institutions. When you're investing in science, it is not a bet. It is, a thought through hedge, and we really hope that there is a lot more that comes in Indian science. Thank you very much for being a most thoughtful audience, and thank you to all the participants and for all your questions, and I'll find a way of getting you an answer.